So I'm so bad about that. I'm so sorry. Okay. All right. So let's talk about chapter 5. We are winding this stuff down. We've talked about lots of different types of functions already. We've talked about polynomial functions and rational functions, and specifically some quadratic functions, and we've talked about root functions and all kinds of lovely things. But what we haven't talked about these exponential functions. Now, exponential functions are different than other functions in that the variable is the exponent. So it might be f of x is equal to or y is equal to. Remember, we can interchange those two things, but we're going to have something raised to the x power. And x is going to be our variable that's going to change. B is going to be a constant. It does have to be positive. It can't be 0, or it has to be, yeah, it can't be 1, and it does have to be greater than 0 or positive. So it might be something like y equals 2/3 to the x power. Okay, so what we're changing is our exponent, and that's why it's called an exponential function. Okay, now it says that b has to be positive. I could have the function that looks like this, -2 to the x power. That is legitimate because -2 is not raised to the x power. Just 2 is raised to the x power. So this is okay. What you can't have is -2 to the x power. All right. So this is not possible. So going back to early days of the semester when we talked about what was actually being raised to the power, this one, the negative is not, this one, the negative is, and I can't have a negative base. Okay. So keep that in mind. All right. Now, there is a very special exponential function, and it is called the natural exponential function. And it is defined where the base is this number e. Now, e is called Euler's number, and Euler's number is kind of like pi. If you remember your pi from like probably middle school days, the little symbol, the pi, this kind of pi, not the apple, blueberry, or blackberry kind. And it is approximately 2 points, not 2 point, hello, that's pi, I mean, that's e, 3.14, 3.141, it keeps going. So my point being is that pi is what we call an irrational number. I don't want you to get confused. Euler's number is another irrational number. It doesn't ever end. So in your calculator, if you put it in there, you get 2.71 and some decimals out here. That is going to give you a better approximation than if you just type in 2.7 into your calculator. So E, like I said, is called Euler's number. It is the base for what we call our natural exponential function. It is just, it's a number that just kind of shows up in various and sundry things, in particular the world of business. When you're talking about interest problems and stuff like that, that's kind of one of those places where it tends to show up. So it's a lovely function, and we're going to talk more about it. So that's our special base. Okay? You should have, if you have this kind of calculator, there is probably this little LN button, which is right there. And it's the second function of that. You'll see an E to the X button. So if you want to look at your calculator, then that might be helpful. So we're going to do some calculator problems here in just a second. Okay. So just to make sure that you can use your calculator, and I know this is a little bit harder with not being face-to-face, but we're going to make this work. So hopefully you have your calculator out. And what I want you to do is I want you to see if you can evaluate 2/11 to the 0.7 power. MyLab's math does ask you to go to 6 decimal places. So that means we need to go to the 7th place and round up. Okay. So I'm going to see if I can share with you guys my calculator. If I have, oh, I don't have a good calculator on here. Never mind. Let's see. No, I do not. I have a terrible calculator on my computer. So never mind. So I can't share my calculator. It's a horrible one. It's okay. We're going to make this work. So what I want you to do is you're going to type in, make sure you put this in parentheses. And I'm telling you to go ahead and do this because I'm going to give you the answer, but then I want to make sure that you're getting that. And if you're getting some weird funky, wonky thing, then we need to talk about what the answer is. So if you do this in your calculator, 2/11 to the 0.7 power, it's going to be 0.3032118113, and it keeps going. But it says 6 decimal places, so that means I need to go 6. I need to go to the 7th. So I'm going to go to this number right here. I'm just reminding you how to round. We're going to go to this number. It's larger than 5, and so my final answer here is going to be, I'm going to put the 0 in front, 3023212, because I'm going to round this up, okay? So go to this 1, the 8 is larger than 5, so that rounds up, all right? So please make sure that you're able to get these answers with your calculator. And if not, then we can talk about how to make this work. All right, so the next one is, I'm going to go ahead and do all 3 of these, and then we can talk about them if you've got questions. So e to the power is where you're going to do that second of that ln function. If you happen to have that on your calculator, you may have an e to the x somewhere else. So in the case of mine, I actually have to type that in first, and then I put in the exponent and close the parentheses around it. And you should get 148 and then 0.43, excuse me, 4131, and it's 591, but so to 6 decimal places, I round to 59. And then the last one has a negative exponent, so just to make sure that you can get that negative exponent typed in, this is going to be 0.81873, and it's 307, so that rounds to 31. You are going to want a calculator for these problems. If for some reason you don't have one handy right now, make sure you're writing all these things down so that when you do get your calculator, you can make sure that your calculator is going to give you the same things that you have on that paper. So, questions about these?
My calculator, when I put in the equation for number 2, all I got was 148.41.
Ooh. Okay. Do you have, what kind of calculator do you have?
TI-30X.
Okay. So do you see the little second button here? And
Yes.
then there's the next button over, it says DRG, and above it, it says SCI.
Yes.
Okay, so hit the second and then that button, and you should get kind of a little menu up at the top that looks kind of like that.
Okay.
Okay, do you see that?
Yes, ma'am.
And what is underlined on yours?
FLOSCIENG.
Okay, which one has the lines underneath it?
FLO.
Okay, that should be good. Okay, and then so when you did the second and the E and the 5, it rounded it?
Yes.
Yeah, it's not supposed to do that, Keaton. Let's see. I know this is like the calculator things, so you gotta love this. This is what calculator day is always like for me. I don't like that one either. Okay, hang on. Okay, do this for me. Push that second and that DRG button and use the little arrows to scroll through and get back to that FLO.
Okay.
And then click equals. And see if maybe you can try that again and see if it likes it better.
Okay, I hit equal, So now I just need to hit second, then hit LN
Yes.
and type in 5, then hit equals again.
Mm-hmm.
And it still gave me 148.41.
Okay, hang on. I'm open to suggestions if somebody else has got the same calculator and can fix this, because we need to fix this. I guess. Oh, I know what it is. Hang on. Okay. Okay. So again, you've got the second, and then down at the bottom, in the middle where the decimal point is, it says FIX.
Yes.
So if you'll do second and then that decimal, you should get something like this across the screen.
Ah, okay.
And what does that say?
F0, 1,
Yep.
2,
What's
3,
underlined?
2.
So use the arrows to go back to F
Okay.
and then hit equals, because that's going to change that to that. And now try it.
There we go. That works.
Yay! Okay. Oh, I'm so proud of myself that I fixed the calculator on the computer. I'm so excited. Y'all think I'm so weird. It's okay. Somebody else probably had the same question. You just don't want to ask. Okay. And somebody else probably had the answer and didn't want to tell me. So whatever. It's okay. All right. Anybody else? See, this is why you should use this calculator, because that's the one I have. And I can do a much better job at that than any of these other nasty things. So I don't like those other ones. Okay. Any other questions on these? But that's huge. If your calculator won't do this, then, oh, goodness gracious, we're going to be here for days. Y'all are going to so not be happy. All right. So, beautiful graph. We can do this. Okay. So on these problems, we are going to be graphing these functions. Exponential functions have a specific shape to them. They are not the shapes we've been looking at. They're not V's, they're not U's, they're not straight lines, they're not squiggly things. They are a curve, okay? And they all have kind of a general similar shape depending upon what the base is. So on most of these problems, it's going to go ahead and give you the 5 x values it wants you to use to complete the table of values. Again, you may not have to fill out both of these columns, but I'm going to fill out both of these. So let's say, for example, I have negative 2 for x, and so this is going to be 3 to the negative second power, which is the same thing as 1 over 3 to the second power, which is 1 over 9. And so I'm actually going to do all of this work in here. So x is negative 2 gives me 1 over 9, and so my ordered pair is negative 2, 1, 9. Remembering that that negative exponent flips it over and becomes a positive exponent, okay? So we'll do the next one here. We have 3 to the negative first power if x is negative 1, which is the same thing as 1 over 3 to the positive first, which is 1/3, okay? So here is my answer for f of x, this one. This is my answer for f of x here. And so my ordered pair is going to be negative 1, positive 1/3, all right? All right, so reminder that anything raised to the 0 power is 1. So when x is 0, I have 3 to the 0 power, which is going to be 1. So I have the point 0, 1. Now, the nice thing about 0, 1 is that this is actually called the y-intercept, okay? And it is going to be something that most of your exponential functions will share, is they'll have the same y-intercept. Because if x is 0, it's going to produce for me a value of 1. Anything raised to the 0 power is going to be 1. So that's kind of nice. Okay. 3 to the first power is our friend 3. So 1, and we have 3. And so I have the point 1, 3. And 3 to the second power is going to be the nice value of 9. And so I'm going to have the point 2, 9. So now I'm going to sketch the graph of this, plotting these points. Now, 1/9 is a little bit hard to plot, so negative 2, positive 1/9. I'm going to point something out to you in just a second. Negative 1, positive 1/3, a little bit bigger. 0, 1, 1, 3. And 2 is way up here at 9. Now, here is what my graph looks like. and it is going to have the same basic shape no matter what my base is. And here's what I want you to see. This graph, these exponential graphs, get close to the x-axis, but they do not have x-intercepts or zeros, whatever we want to call it. There's no way to make this function 3 to a power be equal to 0. I can't raise 3 to a small enough number that I ever turn 3 to a power into 0. So these functions have no x-intercepts unless we add or subtract it. Now, if we were to shift the whole thing down by talking about translations, that would be changing. But for your basic exponential function, which is what we're going to be looking at, you don't have x-intercepts. The domain for these functions is all real numbers. The range for these functions is a round bracket 0 because it can't ever be equal to 0 to positive infinity. Okay, so watch out for that. The range is never going to have a square bracket on it. It's always going to have that nice round bracket. It is going to be 0 to positive infinity. Okay? And in terms of the world of increasing and decreasing, this exponential function is an increasing function. So this particular function increases everywhere. So it increases from negative infinity to positive infinity. So it increases over the entire domain. So as I move from left to right, it goes up. Now we're going to see one in a minute that's going to decrease everywhere. And we'll talk about what causes it to do that. The other thing, notice as my x values get larger, my y values are getting larger. And that kind of just re-emphasizes the fact that it's increasing. Okay. Questions about this one? Okay. Notice that this is the same number, except this is now 1/3 to the x power, where this was a 3 to the x power. That's going to make a big difference, okay? So I'm going to do exactly the same thing, and I chose 3 for both the 1/3 and for the whole number because I wanted you to see what happens with the very similar base. So this 1/3 to the -2 becomes 3 to the +2, 3 over 1, but I don't need to write it over 1. And that's going to give me a y value of +9. Now notice on this one, my -2 produces a large value, or -2 while ago produced a small value, okay? So for the next x value, I have 1/3 to the -1st power. This is going to flip over and become 3 to the +1st power, which is going to be 3. And so I have the ordered pair -1, +3, a little bit smaller, but still a whole number here, and that's important. So I have 1/3 to the 0 power, and that's still going to be 1. So I have the point 0, 1. That's still my y-intercept. 1/3 to the 1st power is going to be 1/3. So here come my fractions now with my positive exponents. And then 1/3 to the 2nd power is going to be 1/9. So when x is 2, y is 1/9. Notice, I hope you're recognizing what's happening. As my x values are getting larger, my y values are actually getting smaller. Not 0, but smaller, okay? So when I graph this at -2, I have the y value of 9. -1, I have a y value of 3. Still have that point 0, 1. At 1, I have the y value of 1/3. At 2, I'm down here at 1/9. And my graph, if I start on the left and I move to the right, notice what my graph is doing. My graph is, you got it, decreasing. Again, it's not ever going to cross or touch this. So this particular graph decreases over the entire domain. So we can also talk about the domain for this function. Any real number can go in there. The range, however, is still just those positive values, not zero. Okay, so does that make sense? So it's a little bit different. Okay, all right. So the 1/3 to the x is a decreasing function. Fraction to a positive x is a decreasing function. 3 to the x is that increasing function. In other words, number larger than 1 to the x is going to be an increasing function. Excuse me. Okay. Questions? Good. I like these as much as anything. Right? Okay. We're done with graphing right now. I want to talk about solving these equations. Okay. So we have two different types of exponential equations to solve. The first way is we're going to solve by using a method called relating the bases. And that's all we're going to do in this section. We've got to learn some other things in order to solve it in a different way. But we can solve exponential functions if we can relate their bases. In other words, if we can make their bases be the same, then we can find the value of x. Okay. Now, for this first problem, you might could look at this and say, I know the answer, and that's great, that's wonderful, but I don't want to do it that way. Okay. I want you to see, rewrite 16 as 2 to a power. So what I have is I have 2 to the x power, and then I want to take 16 and write this as 2 to the, well, 2 squared is 4, 2 cubed is 8, 2 to the 4th power is 16. So 16 is 2 to the 4th power. Now, here's what I need you to see. If I have this so that I have something to the x is equal to something to the y, and these two guys are the same, just like this one and this one, then I can simply say x is equal to 4. And so now my solution is, I don't even have to solve anything, x equals 4. And that's my answer. That's it. I'm done. Okay. Now, could you have looked at this equation and gone, well, I know 2 to the 4th power is 16. Yeah, you could. Could you do that for all of them? Probably not. And so that's why we go through this process. Okay. All right. Okay, excellent. So let's do the same thing over here with number 7. So I have 3 to the x minus 1. 3 is a really nice number, so we're just going to leave that alone. 3 to the x minus 1 power. I want to rewrite 1/9 as 3 to a power. Now, I'm going to remind you over here that 1/9, oops, let's go back over here. 1/9 was 3 to the negative 2 power. Remember, 3 to the negative 2 power simplified to 1/9. See, we've already seen this. I kind of did this on purpose. So I can actually rewrite this as 3 to the negative 2 power. Now, some of you are going, oh, well, what if it's not the one we've already done before? Okay, here's what I want you to do. Think about this as 3 to the 2nd power. So 1/9 is 1 over 3 squared, because 9 is 3 squared. I need to write 9 in terms of 3. But I don't want 1 over that. I need it to be 3. So I can change that into 3 to the negative 2. And that's where this comes from. Okay. So now I have the bases that are the same. I have 3 and 3 here. So that means I can take the exponent of x minus 1, and I can set that equal to negative 2. So x minus 1 is equal to negative 2. Add 1 to both sides. I get x is equal to negative 1. And that is my final answer. Questions? I'm making me a little bit nervous. I got this. Okay. You can type to me in a private chat. I don't even know what to ask. That's okay too. Well, it's not okay, but it's acceptable. I'll accept those. Okay. See, this is what happens when you don't ask questions. I go on to the messy ones. This one's not that bad. I just need to write it so I have E on both sides to a power. So on the the left-hand side, I don't know my left from my right, I'm sorry. I have E to the 5x plus 2. Over here on the right-hand side, the cubed root of E, I can write as E to the, let's see if y'all working, y'all are paying attention. The cubed root is what exponent? Close. I'm going to ask you, see, I knew I was going to get y'all. Remember that x, we'll go with a's rather than x's. We don't want to be anything confused. A to the 1 over n power becomes the nth root of a to the first power. That looking familiar? Oh yeah, light bulbs are coming on. So the cubed root is what exponent? A couple of people were very close. Yes, I got one answer. Let's see if I can get another. That's okay. So this is kind of a big deal, and I'm not seeing a whole lot of answers, so that tells me that I need to go back and really kind of think about this a little bit with y'all. So anytime I have a root here, I can rewrite this as a rational exponent, okay? So my roots become rational exponents. So this cubed root is the 1/3 power, all right? So let's come over here for a second. If I have a cubed root of something, that's going to be the 1/3 power. If I have a square root of something, that's going to be the 1/2 power. If I have a fourth root of something, that's going to be the 1/4 power, okay? Is that starting to remember, strike some little chords of something, hopefully? Okay, so big deal, kind of important. Yeah, you need to know that. Okay, I know it's been so long, like 2 weeks or something. So now I have e's on both sides. I have my exponents, and so I'm going to set my exponents equal to each other. So this is equal to this. I know you thought you were running away from the fractions. I'm so sorry. 5x plus 2 is equal to 1/3. I can subtract 2 from both sides. I get 5x is equal to 1/3 minus 2. I'm going to take all of the fun little amazing steps here. This is 1/3 minus 6/3. Oh yes, I can write a whole number as a fraction over 3. Yes, we can. And so then I have 5x is equal to negative 5/3. Now here's where we got to be a little bit tricky, because I'm going to divide both sides by 5, which is the same thing as multiplying by 1/5. Yes, it is. To divide by a number is the same thing as multiplying by 1 over that number. And so now I'm going to get x on this side and negative 1/3 on this side. Things simplify out, don't lose your negative. So x is negative 1/3. Now is a fabulous time to ask any questions you might have on fractions.
How did you get 6/3?
That's a great question. So I want to take 2 as a whole number and write it as a fraction over 3. And the reason is because I need common denominators. So think of this as 2 over 1. Any whole number can be a number over 1. So 1 divides into 3 times, and 3 times 2 gives me 6, okay? Or I can think of multiplying numerator and denominator here by 3 over 3. So that gives me 6 over 3. That strikes some little memory chords, hopefully. Here's the other really super positive thing I will tell you guys, because at this point, I mean, I don't care. I'm good with this. If you type 1 divided by 3 in your calculator, it gives you a decimal. And then if you say -2, it gives you this really messy decimal there. Okay. But I'm going to show you how to get rid of the decimal and make it a fraction. Oh, yes. I'm going to show you how to use your calculator. So there is this right below, it's this little button right here. Okay. So you have to do second and then that button. And it's going to produce for you the mixed number. And then there's a second button on here. It's this one right here. And if you do second and that, so second and, oops, that, it gives you, yep, I don't know whether you can see it with the glare. It gives you the actual fraction. Okay. So hopefully that may help too. So, clear forward. Right. So you can actually do that on your calculator. All right. So now I'm going to have to drag a few more things out of your memory banks. I know this is not your most favorite part, but watch this real quickly. One more refresher. So here's another remember when. So remember that if I have, let's say, x squared raised to the 3rd power, do you remember what we do with these exponents? We multiply them. So I have x to the 6th power. Well, here I have e to the x squared squared. So I have to multiply 2 times x squared. So this becomes e to the 2x squared power. Okay, don't multiply these exponents. This is my exponent, x squared, times this exponent of 2, so it becomes 2x squared. Okay, and that's equal e to the 8th power over here. All right, be really careful there. Okay, here is my exponent, and I'm multiplying it by this exponent. So multiply exponents, and that's going to give me 2x squared. So now I have like bases, and so I simply take the exponents and set them equal. So 2x squared is equal to 8. X squared is equal to 4. And x is equal to both positive and negative 2. So I actually have 2 solutions here. Okay. X is equal to negative 2 and positive 2. Questions? That's probably the hardest one of these we did, just because you have to remember those rules for exponents. You're doing great. Loving these. Okay. Big formulas. I will give you this formula. I will not tell you what everything is, but I will give you the formula on the test. Okay. The quiz, I think some of the quiz questions actually tell you what everything is. Whatever. Okay. Homework and quizzes, you need to have your formula available to you in case it's not on there for some questions. But I will give you this formula on the test. Promise, guarantee, we'll give it to you. Will I tell you what everything stands for? No. Will I tell you a couple other things? No. You will have to know some things. Okay. So what happens when you invest money in the bank? You take your money, you put it in the bank, you say, okay, I need it to earn more money. Easiest way in the world to make money is to let your money make money for you. So we take some particular amount and we call that the principal. And after a period of time, we get a new amount. And that's called the accumulated value or the total amount after T years, okay? So sometimes this A is also known as the accumulated value, all right? So what we get at the end, okay? T is time in years for interest. So if you're given 6 months, you have to write T as 1/2. Okay, I'm not going to do that to you on these, but I'm just letting you know. R is your interest rate, and you do have to use this as a decimal. So this must be a decimal. And if you recall, in order to write this as a decimal, we take the interest rate divided by 100, or you move the decimal 2 places to the left, okay? So this is, for example, if R is equal to 5%, then this would be 5 over 100 or 0.05, okay? This is all right? So just remember you have to move your decimal. So N is the really only thing you have to remember in these. And N is the number of times that the interest is compounded yearly or annually. So what happens is your interest earns more, or your money earns more interest. So with simple interest, which we've talked about, simple interest is just you take money, it earns interest. The end of the year, you get the interest. That's life is good. What happens with compounded interest is you invest a certain amount, it earns some interest. After a particular time period, that interest is added back to what you started with. And so then the next time the interest is calculated, it's calculated on the new amount, the principal plus the interest. So each time your interest is calculated, it's calculated on a larger sum of money. Therefore, you end up with more money at the end. The N is how many times that happens every year. So there are 4 things that we're going to talk about, okay? So if, and we're going to come over here and I'm going to make, this is for N, all right? So if it says compounded annually, well, if something happens annually, it happens once a year, so N would be 1. If it tells you that your interest was compounded semi-annually, N is going to be 2 because it's twice a year. Lots of people have a semi-annual sale. That means they have it twice a year, okay? I know, I'm all about the sale things. If it says compounded quarterly, right? Quarterly means, it actually means every 3 months, but it means 4 times a year. So N is going to be 4, just like there's 4 quarters in a dollar, there's 4 quarters in a year, okay? And then finally, it says, it could say compounded monthly. And I always ask this question in class because it amazed me. One semester, somebody told me 13 months were in the year. No idea what planet they were on. But anyway, the last time I checked, there were only 12 months in our calendar year. So that means every month it's going to be compounded. So that would be 12 times a year. So you do have to know these 4. So if you see in the problem compounded annually, you're going to let N be 1. Compounded semi-annually, N is 2. Compounded quarterly, N is 4. Compounded monthly, N is 12. Okay? So otherwise, you'll just have the formula, but you're going to need to know this. All right, let's see if we can use the formula. If you don't have your calculator, go get it. You're going to need your calculator on these problems. Okay? So problem number 1 here says find the accumulated value. So this is A of an investment of $9,000. So here is P for 10 years. Here is T at an annual interest rate of 3.5%. So that means R is 0.035 if the money is compounded quarterly. Quarterly means N is what? Somebody help me.
4.
Exactly. Thank you very much. Okay. 4 times a year. All right. And now we're going to plug and chug. We're looking for A. So A equals 9,000. 1 plus 0.035 divided by 4. Raised to the 4 times 10 power. Now, I am going to offer you a huge word of caution. You can put this straight into your calculator, but I am going to tell you to do one thing before you do that, unless you're going to be super careful. Multiply 4 times 10 and get 40, okay? And now literally you can type that into your calculator just like it is. You can use parentheses and everything will be amazingly wonderful. If you don't get the same thing that I'm going to show you, then we need to talk about why, but I think we'll probably be fine. This is going to give me $12,752. And I round to 2 decimal places because I'm talking about money. And so it's 179, so I round it to 18 cents. Questions? Please make sure you get that. If you do not, let me know what I need to get. Justin, you're quiet today. You there? Okay. All right. Everybody okay on this? All right. Y'all are great. Y'all are just, y'all either don't have your calculators with you or you got this calculator stuff down pat. That's amazing. Okay. So I think you can probably punch and crunch into your calculator. So we're going to talk about the second interest formula. Again, I will give you this formula. I will not tell you what everything is, but I will give you the formula. What happens is if that N gets sufficiently large enough, in other words, if the number of times it's compounded gets to be such a huge number, then we have to use a different formula. And what we say is that the interest is literally being compounded continuously, okay? It's a lovely concept. We talk a little bit more about this in business calculus as to how this actually works, okay? But for right now, you just need to know we have a different formula. So notice there is no N here. So if it says continuously compounded, then this means there is no N. Okay, so N's not equal to anything, so we don't have to worry about N, okay? A is still our total amount or our accumulated value. P is still our principal. R is still the interest rate. Remember, we've got to make this a decimal. And T is still time in years. E is that lovely little thing we've just been talking about, okay? So let's look at a problem. So problem says, find the accumulated value of an investment of $6,000. So we're looking for A. Here's our A that we're looking for. Here is our amount, our principal. Time is 20 years. Interest rate is going to be 0.0625. Yep, 2 decimal places. I don't care how many are there. And here is our formula. Round to the nearest cent. That means 2 decimal places. Okay? So A equals 6,000 times E to the 0.0625 times 20 years. Okay. Now you can, I can't ever tell if this is what's the best way to do this. So whatever works for you, you have to multiply these together, but this has to be in parentheses. Absolutely has to be in parentheses. So if your calculator, and this little one that I keep showing you, it automatically puts a parentheses up there, and I think that's amazing. So, but if it doesn't, you need to make sure you open a parentheses and multiply that together. Better yet, I would probably multiply those two things together first and get, in this case, 1.25, and then do all of this at once. But you can do everything at once. It's okay. So 6,000 and then times e to this lovely exponent, 0.625 times 20 power, and we get $20,942.06. So after 20 years, our interest, our money grows quite nicely. Questions? How we doing? Okay. So this is our non-interest application problem. And I really just wanted you to see that we actually do use these exponential functions in things other than interest problems. And that's because that's probably the primary place that you see these exponential functions, at least in this class. But when you get out into the real world, a couple of y'all are kinesiology majors. I mean, this is a legit kind of problem. I don't think I have any wildlife fisheries majors, but exponential functions tend to be in things like population extinctions. You need to worry about when a population is going to need to be put on an endangered species list. If you happen to be a sociology major and you're worried about what's going to happen, when a population is going to explode, when they're going to outgrow a particular place, exponential functions. We're kind of hoping that COVID-19 becomes a decreasing exponential function, but I mean, right now it's kind of an increasing function. So anyway, hopefully it won't be there much longer, but it's, I mean, that's a real life exponential function, folks. So anyway, or it was for a little while. It's kind of started to level off, so not necessarily exponential, but you start to see these things in real life places. So I wanted you to see an example of when you might see that. So most people who start a serious weightlifting regime initially notice a rapid increase in the maximum amount of weight they can bench press. So after a few weeks, this increase starts to level off. And so the following function is going to model for us the maximum weight W that a person can bench press in pounds at the end of T weeks of working out. So the first question says, what was the maximum weight that this person could bench press initially? Well, initially is when T is 0, okay? And so what this is asking me to do in disguised method is to find W of 0. So that means I would put 0 in for T. So I have 250 minus 120 times e to the negative 0.3 times 0 power. Well, we're going to actually do this part without a calculator. So 250 minus 120 times e to the 0 power. Well, e to the 0 power, just like anything else to the 0 power, is 1. And so I have 250 minus 120. Order of operations says I need to take this product before I subtract. And so this particular person started off this program and they could bench press 130 pounds. Okay, so the initial bench press is 130 pounds. Now, after they started working out and practicing and all of this, after 3 weeks, we want to see what the maximum weight they could bench press was. So now we need to find W of 3. And so 250 minus our 120 times e to the negative 0.3 times 3 power. Remember, do this together. Put it in parentheses if you need to, okay? Order of operations is going to tell us to take care of that exponent first, and then take care of the multiplication, and then take care of the subtraction, or your calculator will allow you to do all of this at once. And this is going to be 201.21 pounds. And I'll show you that little intermediate step in here. This is 48.7. But if you can punch it all into your calculator at once, that's fine. Questions? Okay, that's the end of exponential functions. It's the end of section 5.1. So the next thing we're going to talk about ties this back together with section 3.5, 3.6 inverse functions. Sorry, I couldn't remember the section. Okay, so come on. All right. So now we're going to talk about the inverse of exponential functions, which are called logarithmic functions. And your calculator will do some of these and not all of them. And I'm going to show you how to use your calculator for these. But the big thing is you need to know what this relationship is. If you recall, when we found inverse functions, we flip-flopped the x's and y's, and then we solved for y in order to put it into a form that we could recognize as a function. Well, that's what a logarithmic function is. It is the inverse of an exponential put into a form that's solved for y. So we read this as y equals log base b, just like the base for our exponent, of x. And so I always like to tell people that. So y is log base b of x. That's how I read that statement, okay? And that statement is actually equivalent to this exponential form. So if you recall, real quickly, y equals b to the x, that was our exponential equation, right? The inverse of this would be x equals b to the y. And lo and behold, that's what I have here, okay? So this is the inverse of this function. Just what we did in section 3.5. We flip-flop the x's and y's. And then some lovely person came along and said, oh, let's write it and solve for y. So now we need this new function. And this new function is called a logarithmic function, okay? LOG for short. So what you need to know is that if I have a logarithmic function, the value for my logarithm is the exponent for my base, okay? So a logarithm is actually an exponent. Our base has to be positive. The domain for my logarithm has to be positive, and that's because that's all that ever comes out of this, okay? And base can't be 1, okay? So we're going to take this, and I'm going to show you a couple of different ways to do this, and we're going to rewrite this several times. We're going to do a lot of manipulation in this section. exponent form to logarithmic form to exponent form, back and forth, back and forth, back and forth. And we're going to use these to evaluate. We're going to do all kinds of amazing things with it. Okay. So, but I'm going to show you one other thing that we can do. So I can also write this as log base b of x is equal to y. And here's what happens. My base gets raised to this power, and it's all going to be equal to this number. So it kind of makes a little bit of a circle. So b to the y is equal to x. Okay, so we lose the logarithm. So when it goes into exponential form, LOG's gone, right? Okay, let's see what some amazing things we can do on. Okay, restated this for you so that we can follow along. All right, so my exponential form, 3 to the second is equal to 9. I want to write the logarithmic form. So over here in this column, we're going to have the logarithmic form. So it's going to look like this, okay? So looking at 3 to the second is equal to 9, somebody tell me what the value of y is in my exponential form so that I can start to write the logarithmic form. What is y? Matching things up, think about picking this up and setting it down on top of this. What lines up with the y? Can you just chat it to me?
The second power?
Yes, the 2. That's it, just the number 2. Exactly. So 2 equals, and then we write that LOG, right? Looking at this and looking at my formula up here, what number represents B? Yep, somebody chatted it to me. It's a 3. And that means the only thing I have left is my 9. So this is the logarithmic form. I could also write the LOG part first. So log base 3 of 9 equals 2. It doesn't matter whether the y is on the left side or the right side when I write this, okay? It's just that the exponent, this guy right here, has to be what the logarithm is equal to, all right? So make sure. Okay, so I'm going to give you all a second to write the next one. I'm not going to make you type it to me. I'm just going to ask you to tell me what goes in some specific places. So rewrite this one, lining up the different pieces. What is y? What is x? What is b? Okay, so here we go. Already, I need you to privately chat to me what goes on the side by itself. In other words, what is going to be equal to log something? What's going to go over here by itself? Yes, 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 yes. Excellent, excellent. Ooh, not quite. Oh, I get you. Okay, I see what you're saying. Okay, all right. Yes, yes. Yeah, okay, not sure it's okay. All right, so 3 here, let me see if I can color code these for you. So 3 matches with the y, and that's going to be my number here. So -3 is equal to log base. So now here we're going to go log base. Here's my base, and it's going to be right there. And so log base 2 of, and let's go, x is my 1/8, and it's going to be here with the logarithm. Okay, so -3 equals log base 2 of 1/8. okay? My base should be pretty easy to find, okay? So let's do this next one a little bit differently. Let's start with the logarithm. So log base, what is my base for my logarithm? In other words, what is the base for my exponent form? Yep, I see one right answer. If I can get a couple more. Yep, yep, yep. See if we can get one more. Matching this guy up with this one. What's here? Yep, that would be log base 7. Okay, now flip-flop these two. If 7 has the 5K beside it, I don't want the 5K there. So what's going to go here is going to be L, and this is going to be equal to 5 times K. Okay, so this is, and like I said, you can write it as 5K equals log base 7 of L. It does not matter whether the 5K goes on left or right, as long as the log base 7 and L go together. We're going to flip-flop this process next, so just beware. All right. So now we're going to go from the logarithmic form into the exponential form. Now, notice the way all three of these problems are written. It's actually written so that we have log base b of x equals y. So if that's throwing you off that the y came first, then just flip-flop it around. That's okay. All right. So here's where I was talking about the little circle thing. So I can actually do that little circle thing here if you want to. So my base, here's my base, 5 to the value of the logarithm is 0. So 5 to the 0 is equal to 1. And here's where I was talking about that circle. So I have 5 to the 0 power equals 1. So 5 to this power, these two guys go together. I skip this one, equals to the other number. Okay. Some people like the circle. So some people don't. Some people just like to memorize it. All right, so let's see where we are. What is the base for my exponential on number 5? What is my b value? Send me what you got. Yes, 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 yes. I love it when my light bulbs come on. Yes, yes, yes. Okay. 4. What is my exponent? What's going to go here? Yes, yes. Yes, yes. Have confidence. No question marks. 4 to the L. And this is all going to be equal to K. Right? So 4 to the L power equals K. Okay. All right, last one of these. So again, we have our base, in this case of A, to the power of 3 is equal to x minus 1. So that looks a little bit different because we have something other than just a number there, but it works the same. Logarithm to exponent. We did exponent to logarithm, now we're logarithm to exponent. Questions, questions, questions. Okay. So now we're going to talk about how to evaluate these guys without your calculator. Your calculator will do some logarithms. It will do an log, which is special, and it'll do an ln, which is special. But log base 2 is not so super special. So I'm going to show you how to do these without your calculator, okay? And we're going to do these by rewriting them or thinking about them in terms of an exponential form. And so remembering that the value of my logarithm is my exponent. When I try to solve this, I can actually say this is equal to y, because I don't know what y is. And so I can rewrite this as 2 to the y power is equal to 8. And then you would be able to tell me that y has a value of what? 2 to what power is equal to 8? Somebody help me out. Yep. 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 Okay. So my answer here is going to be 3. Okay. So you can either rewrite it in the exponential form and think through that process, or sometimes you might be able to simply say 2 to the third power is equal to 8. I'm done. Okay. So 3 to the what power is 1/9? Anybody know? 3 to what power is 1/9? We kind of beat this one to pieces today, so you might know this one. 3 to what power gives me 1/9? I got a couple of right answers, a couple of not quite right answers. I think I know where you're coming from on that one, but okay. So think of this as 3 to some power is going to give me this fraction of 1/9. Well, first thing I need you to recognize is I'm turning a whole number into a fraction, so my answer has to be negative. And then 3 to the second power, 3 times 3 is 9, but I need that exponent there. And so since I have 3 times 3, it means I have 2 3s. And so 3 to the second power. And so my answer here is going to be negative 2. All right. So this one's a little bit tricky because I've got 6 to some power is the cubed root of 6. But we talked about this like, I don't know, 30 minutes or so ago. What is my exponent that represents the cube root? Yes! I'm so excited. Yes, 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 yes. Some of you guys who are not having confidence are having some confidence. You're getting this. I'm so excited. Okay. Last one of these, and then we'll talk about some fun things. Okay. This one is similar to number 8 in that I have 4 to a power is going to give me this fraction of 1/64. So what kind of answer is going to, what kind of exponent is going to take 4 and turn it into a fraction? Yep. It's going to be negative. Okay. And then 4 to what power is 64? And that answer would be a 3. And so 4 log base 4 of 1/64 is negative 3. How are we doing? Don't think too hard. That's the best advice I can give you about logarithms. Don't think too hard. Value of the exponent is the value of my logarithm is an exponent. 4 to what power gives me this number? All right. There are a couple of little properties that just make your life easier in terms of these. And so you can go back and use exactly what we did on the previous page. Or if you can remember a couple of these, they just, like I said, they just make life nice. So if I have log base any number of that same number, so like here, log base 5 of 5, that's going to be 1. Done. There's nothing else you have to do to it, period. It doesn't matter what these two numbers are. If they match up, I just get 1, okay? If I have something where the two things match up, but there's an exponent here, for example, log base 7 of 7 to the -4th, then this stuff all becomes 1, cancels out, and it simply leaves me with my exponent. And that's it, okay? It could be an X, it can be a number, it doesn't matter. All of this stuff is going to disappear and leaves me with my exponent. If I flip-flop this and put my logarithm as my exponent, so b to the log base b of x, then again, if those two things are the same, they cancel out. And in this case, like this one, it leaves me with 11. And then finally, my very favorite one is that if I have log base anything of 1, that value is always 0. So log base 8 of 1 is 0. Log base 10 of 1 is 0. Log base 5 of 1 is 0. Whatever this base is of 1 is always going to be 0. Why is that? Because 8 to the 0 power is 1. Anything to the 0 power is 1. It's so nice. Oh, I think it's going to rain again. Questions? Love some cancellation properties. Just make life one. Nice. All right. So we have two special cases, and these are the ones I told you your calculator would actually do. We have what's called a common logarithm, and we have what's called a natural logarithm. The common logarithm is the logarithm that doesn't have a base on it. Notice it's log base nothing here. Well, that's because the base is understood to be 10. So you could technically write this as log base 10. You will never, ever, ever see it written like that, but technically you could, okay? The other one doesn't even look like a log. It looks like an ln, or on your calculator, it looks like an in. And this technically is log base e of x. So the natural exponential inverse is the natural logarithm, okay? So the inverse of the natural exponential is the natural logarithm. So these are just two very special ones. Like I said, your calculator will actually do those. Special cases from the previous slide that involve this natural logarithm. The natural log of 1 is 0, the natural log of e is 1, and the natural log of e to the x is x. So in other words, these cancel each other out. Natural logs and natural exponentials wipe each other out. Super nice. This is the one that we will use the most. Guaranteed, you'll use that the most, okay? So for these problems, I simply want you to take the exponential form and rewrite it in logarithmic form. Now for these, this is the same thing as when we did these problems. Exponential to logarithm, okay? So exponential to logarithm. So think exponential to logarithm. That means I need to know what my exponent is. So that's going to be 3 is equal to, and I'm going to write it out like this, log base 10, and then I'm going to get rid of that, of 1,000. And you will never see me write this again like this, and that's not the way it's going to be written in my labs. It's going to be 3 equals the log of 1,000, okay? This is my final answer. We do not write log base 10. Okay? If there's no base, it's understood to be 10. Same thing with my exponential and natural exponential. I'm going to start with my exponent, k, equals, I have log base e, again, I'm never going to write that again, but for this problem I am, of 2. Okay, so as I clean this up, it's k is equal to the natural log of 2. I am going to tell you on your homework, when you start typing things in, some people are like, how do I make it bold? How do I make it bold? It'll automatically bold it, okay? So if you type in L, don't type I doesn't work, L-N, lowercase l-n, it will automatically bold it and let you put things behind it, okay? Log the same way, okay? and then you'll have to use that subscript button to put the subscript on. Okay, so just make sure, just type it in and it's going to happen for you. So you don't have to do anything magical to it. If you type in the IN, it's not going to like that. I'm just telling you, answered that question so many times, LN. Okay. All right. Same thing, just flip-flop this. My base for my exponent, this base is understood to be 10, right? So it's going to be 10 to the power of L is equal to K, right? Remember, 10 understood to this power is equal to this number. Okay. Understood power here, e to the fourth power. So e to the power of 4 equals z. Okay. Right? So we're just rewriting these, all kinds of stuff. Questions? Okay. So the last thing I want to do today, we're not going to do section 5.3. We'll do that tomorrow, and that'll be fine. 5.3 and 5.4 together are very, very, very doable. We could probably finish 5.3 today, but I would just like you to breathe just a little bit, so we'll slow it down just a tiny bit there. Like I said, we won't have any trouble finishing that out tomorrow, so that's not an issue. But I do want to talk about the last couple of things here, and that's because we've been talking about domains for all of our functions, and the logarithms are a little bit special. So if you recall, and I know you're going to hate me, but I'm going to go back to this real quick here. When we first introduced logarithms here, okay, I told you that x had to be greater than 0. That's this guy right here, okay? And that's because the range for my for my exponential function was everything 0 and larger. If you recall, we're just flip-flopping these things, okay? So the important thing is, though, that you can't take the logarithm of a negative number, okay? So if I have this expression in here, in order to find the domain, okay, so to find the domain of a logarithmic function, we take whatever's in here and we set it greater than 0, all right? That means I have to divide both sides by a negative. Remember what happens with my inequality? That flips this around, okay? 0 and negative 0, there's no difference. So for this function, I have to use negative numbers, and that's because I'm changing the sign. This is the log of the negative, or the opposite of whatever I'm plugging in there. And so the domain in interval notation is negative infinity to 0, okay, for the logarithm of negative x. Okay. Notice I don't care what the base is, so I'm going to do the same thing for this one. I'm going to take this little piece in here, okay, and I'm going to take 2x plus 6, and I'm going to set it greater than 0. Subtracting 6 from both sides, I get 2x is greater than negative 6. Dividing both sides by positive 2, I get x is greater than negative 3. So the domain for this function is round bracket 3 to positive infinity. My domains for my logarithm functions, hear me, will always have round brackets, always on both ends. Okay, I'm not going to ever include what makes that 0. Right? All right, last one. I want y'all to do this one for me. And then you can type it into the chat. Oh, yes, we can do this. I need an answer, even if it's a I don't know. I need an answer from everybody. You can even be honest and say, I missed what you said because I went to get a cup of coffee. Okay, okay. Sorry, I'm talking to y'all and talking to myself. Yay! That's what I need. Okay, so I've got some great answers. All right. And I got some folks who are not quite with us, but it's okay. So I'm worried about a couple of people. So but we'll get there. All right. So let's talk about how to do this because I've gotten some great answers. So let's start with, remember, we're looking in here. I don't care what this is. I'm looking inside of this. And I'm going to take what's inside of this and I'm going to set it greater than 0. And I have to solve this inequality. Now, several people did this really great, and some of you got stuck along the way. So the first thing I have to do is subtract 1 from both sides, and that's going to give me negative 3x is greater than negative 1. Okay. Then when I divide both sides by that negative 3, I get negative 1 divided by negative 3, but because I divided by that negative number, this becomes less than. And so when I simplify this, I get x is less than 1/3, and that's fabulous. In terms of my interval notation, though, a couple of people got backwards on this. It's negative infinity to 1/3, and that's it. That's all I can use. That's what my domain looks like. Okay? I love the way y'all got some negative infinities going on here. They're so pretty. Questions? Okay. A couple people are trying to out if you're still in. Elijah, are you still with us? Car Faith, are you still with us? If y'all are, let me know.
Yes, ma'am. Car Faith is still here.
Okay. I just haven't seen from y'all in a little while. All right. Kira, are you still here? All right. Just missing a few folks. Okay. And I don't think Amy, Clarence, Jacob, none of y'all showed up, did you? All right. Just so that you know, the next section is working with logarithms. And so here is my suggestion to you. I know that obviously you want to get homework and quiz number 8 done first, but if at all possible, at least look at homework number 9, just the first couple of problems, or review back over this, because, and that's the other reason I'm stopping today, is because we're going to take the same stuff we did in section 5.2, and we're going to talk about logarithms and talk about their properties and how to expand them and condense them and do some manipulations with them. And then in the last section of this chapter, we're going to talk about solving equations with them. And so it'll just be very helpful to you if, like I said, even if you don't get a chance to look at the homework number 9, the first part of it, at least look back over the notes from section 5.2 before class tomorrow, just because for most people, logarithms is one of those things. Even if we've understood everything we've done up until this point, logarithms are the one thing that you either didn't get taught in high school, or somebody did something hideous and horrible with them and made them make absolutely no sense. And so I think the way we teach logarithms is usually pretty friendly. And most people have lovely light bulb moments. So if you're not having a light bulb moment, you will. So feel free to ask, okay? But just kind of look over that. So don't forget, working on submitting to me questions for the exam review. Those are not due till tomorrow night, so you still got some time on that. Finishing up homework and quiz 8 if you haven't done that, and I know some of you have already started on it, and that's wonderful. And start looking at homework number 9. We're close to the end, guys. Just give me a couple more days and we'll be out of here, all right? So if you've got questions, stick around and ask them. Otherwise, have a lovely Monday. Bye.